Part 1. Into the Abyss. What exactly is a black hole, and why are they so mysterious? Imagine a place in the universe where the pull of gravity is so powerful that nothing, not even light, can escape. A place where time slows down, where space is bent and twisted, and where the known laws of physics break apart. These places are not science fiction, they are real. They are called black holes. A black hole isn't really a hole in the traditional sense. It's a region in space where matter has collapsed into an extremely small volume, creating gravity so intense that everything nearby is pulled in. Once something crosses the invisible boundary surrounding the black hole, called the event horizon, it can never return. That includes spacecraft, planets, light, and even the information that describes them. Black holes are invisible by nature. They do not reflect light, and they do not emit it in any ordinary way. But we can detect them because of what they do to the world around them. We see their effects on nearby stars, gas clouds, and even the structure of entire galaxies. In recent years, we've even managed to capture images showing the outline of a black hole using telescopes spread across the Earth. These are no longer just theories on a chalkboard. They are part of our observable universe. The story of black holes begins with a brilliant idea from Albert Einstein over 100 years ago. In 1915, he introduced a new way of thinking about gravity, not as a force pulling things together, but as the bending of space and time caused by mass. According to his theory, massive objects like stars and planets actually curve the space around them. The more massive the object, the more space bends. And in the case of black holes, space bends so much that it forms a kind of bottomless pit. Shortly after Einstein published his theory of general relativity, a German scientist named Karl Schwarzschild found a solution to Einstein's equations that predicted something shocking. If enough matter were squeezed into a small enough space, it would create a gravitational field so strong that nothing could escape it. This was the first mathematical description of a black hole, but back then, it sounded more like a strange side effect of the equations, something interesting, but not real. For decades, scientists weren't sure black holes actually existed. They were considered mathematical curiosities, not physical objects. Even Einstein himself doubted they were real. But over time, as telescopes grew more powerful and our understanding of stars deepened, it became clear that black holes weren't just possible. They were necessary. Today, we know that they form naturally when very massive stars die. When a massive star runs out of fuel, it can no longer support its own weight. It collapses in on itself in a violent explosion called a supernova. For smaller stars, this collapse might leave behind a white dwarf or a neutron star. But if the star is heavy enough, many times more massive than our Sun, then the collapse continues, past the point of no return. The core of the star is crushed into an incredibly dense point, and a black hole is born. Black holes come in different sizes. The smallest ones are a few times heavier than our Sun, but only a few miles across. These are called stellar mass black holes, and they form from dying stars. Then there are supermassive black holes, millions or even billions of times heavier than the Sun. These giants sit at the centers of galaxies, including our own Milky Way. The one at the center of our galaxy is called Sagittarius A Scull, and it's about 4 million times as massive as the Sun. There's also something in between, intermediate black holes, heavier than stellar ones, but not nearly as massive as the supermassive giants. These middleweights are harder to find, but scientists are beginning to uncover evidence that they exist too. The full range of black holes tells us something important. They aren't just cosmic oddities. They are everywhere, and they come in many forms. But what really makes black holes mysterious is not just what they are, it's what happens near them. As you get closer to a black hole, gravity becomes stronger and stronger. Time itself begins to slow down. If you could hover just outside the event horizon, someone watching from far away would see your clock ticking more and more slowly. From their point of view, time would almost stop for you. This effect, called time dilation, is predicted by Einstein's theory and has been confirmed in many ways. But near a black hole, it becomes extreme. And if you were to cross the event horizon, you would be pulled inward with no hope of escape. According to our current understanding, you would eventually be crushed at a point in the center called the singularity. This is where the laws of physics, as we know them, completely break down. We don't yet know what truly happens at the singularity. It's one of the great unsolved mysteries in science. Despite how strange they are, black holes are not just theoretical anymore. We've observed the signals they send across the universe. In 2015, scientists using the LIGO Observatory in the United States detected ripples in space called gravitational waves. These were caused by two black holes colliding over 1 billion light-years away. It was the first time humanity had heard the sound of a black hole merger. Since then, dozens more have been detected. Then, in 2019, a global team of scientists released the first image of a black hole's shadow. Using a network of radio telescopes called the Event Horizon Telescope, they captured the outline of the supermassive black hole in the galaxy M87. The glowing ring of light seen in the image came from hot gas swirling around the event horizon. The center of the ring showed the shadow, the area from which no light can escape. That image made history. It was proof that black holes are real, and that our theories had been pointing us in the right direction. It also showed that even something we cannot see directly can still reveal its presence through the way it bends light and space around it. Black holes are also a source of deep philosophical questions. Do they destroy information? Could they connect to other parts of the universe, or even to other universes? Some scientists have suggested that black holes might lead to wormholes, or that they could evaporate over time by releasing a strange form of radiation, known as Hawking radiation. These are not just wild ideas. They are serious scientific theories being explored today. What draws people to black holes, whether scientists or storytellers, is the same thing that makes them so hard to understand. They are the edge of our knowledge. They challenge everything we think we know about time, space, gravity, and reality itself. And yet, we are slowly learning to speak their language. As we continue this journey, we'll begin to ask deeper questions. How are black holes formed? What lies inside them? How do they shape the universe around them? And could they one day help us discover new laws of physics? In the next part, we'll start from the beginning. We'll look at how stars live and die, and how some of them, under just the right conditions, end their lives not in silence, but by collapsing into one of the most extreme objects the universe has ever created, a black hole. Part 2. Formation of black holes. How do black holes come into existence? To understand how black holes form, we need to look at the life cycle of stars. Stars are not eternal. They are born, they live, and they eventually die. What kind of death a star experiences depends almost entirely on one thing: its mass. Mass is the deciding factor between a peaceful fading away and a dramatic, catastrophic collapse. Stars form when huge clouds of gas and dust collapse under their own gravity. As the material falls inward, it heats up, and when the core becomes hot and dense enough, nuclear fusion begins. This fusion releases energy, and that energy pushes outward, balancing the inward pull of gravity. For most of a star's life, these two forces, gravity pulling in and pressure from fusion pushing out, are in perfect balance. But fusion doesn't last forever. The star slowly uses up its fuel, turning lighter elements like hydrogen into heavier ones, such as helium, carbon, oxygen, and eventually iron. Iron is a dead end. Unlike other fusion reactions, creating energy by fusing iron doesn't work. So when iron builds up in the core, fusion stops. Without that outward pressure from fusion, gravity wins. The core collapses. What happens next depends on the star's mass. If the original star was not very massive, maybe up to 8 times the mass of our Sun, it will end its life by shedding its outer layers and leaving behind a dense, Earth-sized object called a white dwarf. If the star is more massive, between about 8 and 25 times the Sun's mass, the collapse is more violent. The core crushes itself into a ball of tightly packed neutrons, creating a neutron star. These neutron stars are incredibly dense. A single teaspoon of neutron star matter would weigh billions of tons. But when a star is even heavier, more than 20 or sometimes even 30 solar masses, the core collapse becomes unstoppable. Even neutron pressure can't hold it up. The matter continues falling inward until it forms a black hole. The outer layers of the star are blasted away in a supernova explosion, one of the most energetic events in the universe. What remains is an object so compact and so dense that it warps space and time around it completely. A stellar mass black hole is born. Most of the black holes we've observed so far fall into this stellar mass category. They tend to weigh anywhere from about 5 to several dozen times the mass of the Sun. Some of these black holes are found in binary systems, paired with a normal star. As the black hole pulls material off its companion, that material heats up and emits powerful X-rays before it crosses the event horizon. These X-ray signals are one of the main ways we detect black holes in space. But there is a gap in our understanding between these stellar black holes and the enormous supermassive black holes found at the centers of galaxies. Supermassive black holes can have millions or even billions of solar masses. The one in the middle of our Milky Way is over 4 million times the mass of the Sun. The one at the center of the galaxy M87, which was imaged in 2019, is about 6.5 billion solar masses. How do black holes get that big? That's still an open question. One possibility is that small black holes grow over time by pulling in gas, dust, stars, and even other black holes. As matter falls in, the black hole gains mass and gets larger. This process is called accretion. If enough material is nearby, the black hole can grow very quickly. But there's a problem with this idea. We found supermassive black holes that already existed when the universe was very young, just a few 100 million years after the Big Bang. That might not have been enough time for small black holes to grow that large by accretion alone. So scientists have proposed another idea, that some black holes may have formed in a completely different way. These would be called direct collapse black holes. Instead of starting as stars, these massive black holes might have formed directly from gigantic clouds of gas that never became stars at all. Under the right conditions, such a cloud could collapse straight into a black hole, with a mass of thousands or even hundreds of thousands of suns. This would give it a head start on becoming supermassive. Another possibility is that some intermediate mass black holes, those between about 100 and 100,000 solar masses, merge together over time, slowly building up the mass of the central black hole. These intermediate mass black holes are hard to find, but recent data from gravitational wave detectors like LIGO and Virgo suggest that they might be out there, merging and growing. There's even a more speculative idea that some black holes were born not from stars or gas clouds at all, but from the earliest moments of the universe. These are called primordial black holes. They may have formed just fractions of a second after the Big Bang, when regions of the universe with slightly higher density collapsed under their own gravity. If they exist, they could range in size from tiny to huge. Some theories even suggest that primordial black holes might make up some or all of the mysterious dark matter that fills the universe. But so far, there is no confirmed evidence that they exist. Whether formed from dying stars, collapsing gas clouds, or the ancient chaos of the early universe, black holes are born in extreme conditions. Once created, they become permanent features of the universe, unless something causes them to evaporate or merge. They can sit quietly for millions of years, or blaze with energy as they feed on surrounding material. They can wander alone, or anchor entire galaxies. And when they merge with each other, they send ripples through space itself, waves of gravity that we can now detect on Earth. The formation of a black hole is one of the most dramatic events in nature. It marks the end of one kind of object, a star, and the beginning of something entirely different. A black hole is not just the corpse of a dead star. It is a region of space where gravity reigns absolutely, and where the normal rules of matter, time, and energy begin to fall apart. Understanding how they form is the first step toward understanding the more complex and mysterious behavior that follows. Part 3. Anatomy of a black hole. What's inside a black hole, and can we even know? When people picture a black hole, they often imagine a kind of vacuum cleaner in space, sucking up everything in sight. But the real structure of a black hole is far more precise and stranger. While we can't look inside a black hole in the usual sense, we can describe what we understand about its boundaries, its visible effects, and the extreme physics that define its surroundings. The outermost boundary of a black hole is called the event horizon. This is not a solid surface. There is no wall or shell you would bump into. Instead, it's a region of space where the escape speed, the speed required to break free from the gravitational pull, reaches the speed of light. Once anything crosses this invisible boundary, light, gas, or even a spacecraft, it can never return. From the outside, no information from beyond the event horizon can reach us. It marks the edge of no ability, the point of no return. Just outside the event horizon, black holes often display something spectacular, an accretion disk. This is a swirling, flattened ring of gas and dust that spirals inward, heated by intense gravitational forces. As the material accelerates and compresses, it becomes extremely hot, millions of degrees, and emits enormous amounts of energy, particularly in the form of X-rays. These emissions make it possible for astronomers to detect black holes, even though the holes themselves are invisible. The more massive and active the black hole, the more violent and bright the accretion disk. In some cases, especially around spinning black holes, we also see relativistic jets. These are narrow beams of particles and radiation that shoot out from the poles of the black hole at nearly the speed of light. Despite the name, these jets don't come from inside the black hole itself. Instead, they're launched from the surrounding accretion disk by intense magnetic fields. These jets can stretch across thousands of light years, lighting up intergalactic space and shaping the environments of entire galaxies. At the center of a black hole lies the singularity, a region where our known laws of physics seem to collapse. The singularity is the point where all the mass of the black hole is concentrated. According to general relativity, the singularity has infinite density and zero volume. That means gravity is infinitely strong, and space and time become meaningless. But here's the problem. Infinity is a red flag in science. It tells us that the theory we're using, Einstein's theory of gravity, has hit its limits. We need a new theory, possibly one that combines general relativity with quantum mechanics, to understand what really happens at the core of a black hole. Even before we reach the singularity, strange things happen to time and space. Near the event horizon, time begins to slow down. This isn't science fiction. It's a real effect of gravity on time, predicted by Einstein and confirmed by countless experiments. The closer you get to a massive object, the slower time moves compared to someone farther away. Near a black hole, this effect becomes extreme. For an outside observer, time appears to nearly stop at the event horizon. But for someone falling in, time seems normal, right up until they cross the horizon and head toward the center. And then there's spaghettification, a dramatic word for a real process. Because gravity gets stronger the closer you are to the black hole's center, your feet would be pulled more strongly than your head if you were falling in feet first. This difference in gravity, called a tidal force, stretches your body out like a piece of spaghetti. The same fate would await a star, a planet, or even a cloud of gas if it ventured too close to a small, dense black hole. For larger black holes, the tidal forces near the event horizon are gentler, so you might cross it without noticing anything strange at first. Black holes also come in different shapes, or more precisely, different configurations. The simplest kind is a non-spinning, uncharged black hole, described by the Schwarzschild solution. It has only one defining property: mass. Add spin, and you get a Kerr black hole. Add electric charge as well, and you get a Reissner-Nordstrom or Kerr-Newman black hole. In real life, most black holes are expected to be rotating due to the angular momentum they inherit from the stars or matter that formed them. This rotation affects the geometry of space around the black hole, and can even create a region outside the event horizon called the ergosphere, where space itself is dragged along with the spin. It's important to understand that black holes are defined not by what's inside them, but by what's outside. Once something falls past the event horizon, we can't observe it. We can't measure it. All we can know are the basic features that black holes reveal: mass, spin, and possibly charge. This leads to a famous phrase in physics: black holes have no hair. In other words, from the outside, black holes are astonishingly simple. No matter what fell into them, a rock, a planet, or a library full of books, the end result is the same: an object defined only by a few basic quantities. But that simplicity is deceptive. Inside, or perhaps in the process of falling in, information seems to disappear. According to quantum mechanics, information about a system's initial state should never be lost. But black holes appear to destroy information, or at least hide it in ways we can't explain. This has led to one of the greatest puzzles in modern physics: the black hole information paradox. If black holes truly erase information, our understanding of how the universe works is incomplete. If they don't, then where does the information go? Some scientists believe that the information might be stored on the event horizon itself, in a kind of hologram, a two-dimensional surface encoding three-dimensional data. Others think that black holes might emit information slowly through what's known as Hawking radiation, a faint glow that causes black holes to shrink over incredibly long periods of time. But this radiation appears to be random and doesn't seem to carry any information, at least not as we currently understand it. We're still a long way from solving these questions. But what we do know is this: black holes are not simply voids in space. They are incredibly dynamic and complex. They twist space, stretch time, and challenge the most fundamental rules of reality. They are not just leftovers of dead stars. They are engines of cosmic change, anchors of galaxies, and perhaps keys to unlocking a deeper theory of the universe itself. What lies at the heart of a black hole remains unknown. It may be a singularity, it may be a doorway to something else entirely, or it may be a region where our current science simply fails. But even without answers, black holes continue to teach us. By studying what we can see, light from the accretion disk, the shape of the shadow, the patterns of merging black holes, we get closer to understanding what we cannot. Part 4. Time, Space, and Gravity near a black hole. What happens to time and space around a black hole? Gravity affects more than just how objects fall. According to Einstein's theory of general relativity, gravity is not really a force at all. It's the bending of space and time, caused by mass and energy. The more massive an object is, the more it curves the space around it. Near a black hole, this bending becomes so extreme that space and time behave in ways that seem almost impossible. The closer you get to a black hole, the more reality itself begins to stretch, twist, and break away from ordinary experience. Let's begin with time. In everyday life, we think of time as something steady and constant. 1 second is always 1 second. But Einstein showed that time is not absolute. It flows differently depending on where you are and how fast you're moving. Near a black hole, gravity becomes so strong that it slows time down dramatically. If you are floating near the edge of a black hole, time for you would pass much more slowly than for someone far away. If you hovered just outside the event horizon for what felt like a few minutes to you, years might pass for someone observing from a safe distance. This effect is called gravitational time dilation, and it's been confirmed by experiments, even here on Earth. Atomic clocks placed at different altitudes tick at slightly different rates because the clocks closer to Earth's center feel slightly stronger gravity. The difference is tiny, but near a black hole, the effect becomes extreme. Time doesn't just slow, it almost stops. From the point of view of an outside observer, it would seem to take forever for someone to cross the event horizon. But from the traveler's perspective, they cross it in a normal, finite time, and there is no special sign marking the boundary. Now let's talk about space. Black holes don't just pull objects toward them. They actually curve space itself, like a heavy weight on a rubber sheet. If you placed a black hole on this sheet, everything nearby would roll toward it, not because it's pulling them, but because the space is warped. The closer you are to the black hole, the steeper the curve. At the event horizon, space curves so much that all paths point inward. No matter which direction you try to go, you end up moving closer to the center. This bending of space and slowing of time are both part of what scientists call space-time, the idea that space and time are woven together into one fabric. Around a black hole, this fabric is stretched to its limit. In fact, for an object falling into a black hole, the path it follows is called a geodesic, which is the natural path through curved space-time. From the object's point of view, it's simply falling freely, feeling no force. But from the outside, it looks like it's falling into a place where the rules of space and time no longer apply. One of the strangest and most dramatic effects near a black hole is known as spaghettification. This happens because of tidal forces, the difference in gravitational pull between one part of an object and another. Near Earth, these forces are what cause ocean tides. Near a black hole, they can be deadly. If you fell feet first into a small black hole, the gravity at your feet would be much stronger than at your head. The result is that your body would stretch into a long, thin shape like a noodle. You would be pulled apart, atom by atom. That's spaghettification. Interestingly, the size of the black hole matters. A small black hole, just a few times the mass of the Sun, would have such strong tidal forces near the event horizon that spaghettification would happen before you even crossed it. But for a supermassive black hole, like the one at the center of our galaxy, the event horizon is much farther from the singularity. The tidal forces at the horizon are weaker, and you might cross the boundary without feeling anything unusual, until much later, as you approach the center. Another strange effect happens around spinning black holes. These are described by the Kerr solution to Einstein's equations. Spinning black holes don't just pull matter in, they also drag space around with them. This region, just outside the event horizon, is called the ergosphere. In the ergosphere, space itself is being twisted in the direction of the black hole's spin. Any object inside the ergosphere is forced to move in that direction. It's not possible to stay still. This effect is called frame dragging, and it's been measured around Earth on a very small scale using satellites. Near a black hole, it becomes powerful enough to twist entire streams of gas and light. Scientists believe it might be possible to extract energy from the ergosphere by carefully dropping matter into it. This is called the Penrose process, and it's a theoretical way to tap into the rotational energy of a black hole. It may even help explain the powerful jets we see shooting out from active black holes in galaxies far away. As strange as all this sounds, it's not science fiction. Every one of these effects, time dilation, space-time curvature, tidal forces, and frame dragging, comes directly from the equations of general relativity. They've been tested in many different ways, from the bending of starlight around the Sun to the slowing of clocks near Earth. But nowhere are these effects more intense than near a black hole. These extreme conditions offer scientists a unique laboratory. Black holes push our understanding of physics to its breaking point. They show us where our theories succeed and where they begin to fail. While general relativity works incredibly well to describe the large-scale behavior of space and time, it breaks down at the singularity, where quantum effects become important. To truly understand what happens there, we'll need a new theory, one that combines gravity with quantum mechanics. Until then, we continue to study the region just outside the black hole, where we can still observe. By analyzing light from accretion disks, by watching the orbits of stars near supermassive black holes, and by detecting gravitational waves from black hole mergers, we gain more clues about how space-time behaves in these extreme environments. Black holes do not simply sit silently in space. They bend time, twist light, stretch matter, and reshape our understanding of reality. In their presence, the familiar rules of the universe are rewritten. And though we cannot yet peer beyond the event horizon, the very edge of these cosmic giants continues to teach us what space and time truly are. Part 5. Supermassive black holes and galactic giants. What are those enormous black holes doing at the centers of galaxies? At the heart of nearly every large galaxy, including our own Milky Way, lies a giant that is invisible, powerful, and ancient, a supermassive black hole. These titanic objects can be millions, even billions of times more massive than our Sun. They are not the remnants of dying stars, like smaller black holes. They are something else entirely, cosmic engines that may have shaped galaxies from the very beginning. The supermassive black hole at the center of the Milky Way is called Sagittarius A Sinoff. It has a mass about 4 million times greater than the Sun and sits roughly 26,000 light-years from Earth. We can't see it directly, but we know it's there because of how it affects nearby stars. Using powerful telescopes, astronomers have watched stars near the center of the galaxy move in tight, fast orbits, some whipping around this invisible object in just a few years. The speeds and paths of these stars leave no doubt. Only something extremely massive and compact, like a black hole, could cause such motion. And our galaxy is not unique. Virtually every large galaxy studied so far appears to have a supermassive black hole at its core. Some are modest, like Sagittarius A, while others are unimaginably massive. The black hole at the center of the giant elliptical galaxy M87, for example, weighs in at about 6.5 billion times the mass of the Sun. This is the same black hole whose shadow was imaged by the Event Horizon Telescope in 2019, giving us the first direct glimpse of one of these cosmic giants. But how do such enormous black holes form? That's a question scientists are still trying to answer. One theory is that they grew from smaller black holes over billions of years, slowly feeding on gas, dust, stars, and even other black holes. As matter fell in, their mass increased. Another idea is that they started big, forming directly from the collapse of massive clouds of gas in the early universe. Some may have formed from clusters of stars collapsing together, or from giant versions of the stellar mass black holes that formed very soon after the first stars were born. It's possible that all of these processes played a role. What we do know is that supermassive black holes don't just sit quietly in the centers of galaxies. They play an active role in shaping the galaxies around them. When large amounts of gas fall toward a supermassive black hole, it doesn't always disappear right away. Instead, the gas forms a bright spinning disk, the accretion disk, and becomes incredibly hot. The energy release can be so intense that it outshines the entire galaxy. When this happens, we call the galaxy a quasar. Quasars are among the most luminous objects in the universe. They can release 1,000 times more energy than the Milky Way, all from a region smaller than our solar system. This energy comes from the intense friction and compression of matter in the accretion disk, as it spirals inward at high speed. Some of the energy escapes as light, and some is launched into space as powerful jets that shoot out from the poles of the black hole. These jets can travel for millions of light years, blasting through space and affecting other galaxies. The energy released by an active supermassive black hole can push gas and dust away from the center of the galaxy, blowing giant bubbles into space. This can shut down star formation in the central region, changing how the galaxy evolves. In this way, black holes help regulate the growth of their galaxies, acting like a kind of thermostat. If too much gas starts falling in, the black hole flares up and pushes the gas away. Once the gas is gone, the black hole goes quiet again. This delicate feedback loop might be one of the reasons why galaxies and their black holes grow together. In fact, observations show a surprising connection between the mass of a galaxy's central black hole and the properties of the galaxy itself, especially the bulge or central region. Even though the black hole is tiny compared to the whole galaxy, its mass seems tightly linked to the mass of the bulge. This suggests that galaxies and black holes don't just coexist, they evolve together. It's still not fully understood how this relationship forms, but it tells us that black holes and galaxies are deeply connected. Sometimes, black holes and galaxies collide. When two galaxies merge, their central black holes slowly spiral toward each other, surrounded by clouds of gas and stars. Eventually, they merge into a larger black hole, sending out powerful gravitational waves in the process. These mergers may explain how some supermassive black holes grew so large over time. And in the distant future, our own Milky Way will collide with the nearby Andromeda Galaxy. When that happens, about 4 billion years from now, our two central black holes may eventually merge as well. But even when they're not actively consuming matter, supermassive black holes influence the structure of their galaxies simply by being there. Their immense gravity helps anchor the galaxy's core. They shape the motion of stars and gas around them, and when they do flare to life, their radiation can light up the universe. In the early universe, supermassive black holes may have played an even more dramatic role. Some of the brightest quasars we see formed when the universe was less than 1 billion years old. That means these black holes had to grow very fast. Their jets and radiation may have helped reheat the universe after the cold, dark period following the Big Bang. They may have stirred the gas that later formed galaxies and stars. In this sense, black holes didn't just grow inside galaxies. Galaxies may have grown around black holes. This idea flips the old story on its head. For a long time, scientists thought of black holes as the end of a process. What happens when a star dies or when a galaxy settles down? Now, we're beginning to think of them as architects, shaping the universe from its earliest days. Supermassive black holes are some of the most powerful, mysterious, and influential objects in existence. They are not just strange side effects of gravity. They are central to the structure and history of the universe. They teach us that gravity, on its largest scales, is not just about falling apples or orbiting planets. It is about the formation of cosmic giants, the birth of galaxies, and the long dance of matter across billions of years. Part 6. Black hole observations and breakthroughs. How do we see the invisible? Black holes, by their very nature, are invisible. They emit no light. They reflect nothing. Once something crosses their event horizon, it vanishes from view, leaving behind no trace we can see with ordinary telescopes. And yet, we've managed not only to detect black holes, but to study them in astonishing detail. Over the last few decades, and especially in recent years, science has made incredible breakthroughs in black hole observation. Today, we don't just believe in black holes. We measure them, watch them interact, and even listen to the waves they send through the universe. The key to seeing the invisible lies in looking at what a black hole does to its surroundings. One of the most powerful tools astronomers use is the study of X-rays. When matter falls toward a black hole, it usually doesn't drop straight in. It spirals around, forming an extremely hot, fast-moving disk called an accretion disk. Friction and gravity heat this disk to millions of degrees, and it begins to glow, especially in high-energy light like X-rays. Space telescopes like NASA's Chandra X-ray Observatory and ESA's XMM Newton can detect this radiation, revealing where black holes are actively feeding. Sometimes black holes are found in binary systems, where a normal star orbits alongside an invisible companion. If that companion is pulling material from the star and glowing brightly in X-rays, it's a strong sign that it's a stellar mass black hole. Dozens of such systems have been found in our galaxy alone, and more are being discovered every year. But black holes also make their presence known in ways that have nothing to do with light. One of the most revolutionary discoveries in astronomy came in 2015. When scientists working with the LIGO Observatory in the United States detected gravitational waves for the first time. Gravitational waves are ripples in the fabric of space itself, caused by the acceleration of massive objects. In this case, the waves came from the collision and merger of two black holes over 1 billion light-years away. The signal lasted just a fraction of a second, but it matched perfectly with predictions from Einstein's theory of general relativity. It was a tiny disturbance, stretching and squeezing space by less than the width of a proton, but it was unmistakable. For the first time, we were not just seeing black holes. We were hearing them. Since that first detection, dozens more gravitational wave events have been recorded by LIGO and its European partner Virgo. Each one reveals something new. We've seen black holes merge with other black holes, with neutron stars, and perhaps with objects we don't yet fully understand. These observations allow scientists to measure the masses and spins of black holes, to learn how common mergers are, and to explore the final moments before two titanic objects collide and become one. Then, in 2019, the world saw something even more dramatic: the first ever image of a black hole's shadow. This groundbreaking image was captured by the Event Horizon Telescope, a global network of radio observatories working together to create a planet-sized telescope. By combining signals from telescopes across different continents, scientists achieved an astonishing level of detail, enough to see the silhouette of the black hole at the center of galaxy M87. What they saw was a glowing ring of light with a dark center. The light came from superheated gas swirling around the black hole at nearly the speed of light. The dark area was the shadow, the region from which no light could escape. Its size and shape matched predictions made by Einstein's equations almost perfectly. This was not just an artistic rendering or a simulation. This was a real image, made from real data, showing a black hole more than 50 million light-years away. The achievement was historic. For the first time, humans had captured a direct view of one of the universe's most mysterious objects. The team behind the discovery won global recognition, and the image became a symbol of how far science and technology have come. But these are not the only tools scientists use to study black holes. Observatories like the Very Large Telescope in Chile and the Keck Observatory in Hawaii have been tracking stars near the center of our own galaxy for years. By watching their orbits, how they speed up, slow down, and change direction, astronomers can map the gravitational pull of the invisible object they're circling. From this, we know that Sagittarius A Nauta, the supermassive black hole at the heart of the Milky Way, has a mass of over 4 million suns. Other techniques include radio astronomy, which looks at emissions from gas clouds and jets near black holes, and infrared observations, which can see through dust clouds to the crowded centers of galaxies. Together, these tools allow scientists to build a complete picture, not of the black holes themselves, but of the immense influence they exert on everything around them. And the breakthroughs keep coming. In 2020, the Nobel Prize in Physics was awarded to 3 scientists for their work on black holes. One of them, Reinhard Genzel and his team, had tracked stars orbiting Sagittarius A Tar. Another, Andrea Ghez, had done the same with a different team. Their independent results confirmed that our galaxy's central object had to be a supermassive black hole. The third, Roger Penrose, had shown decades earlier that black holes are not just theoretical possibilities. They are inevitable given Einstein's laws. We are now entering an era of black hole astronomy. Future observatories, like the James Webb Space Telescope, the European Extremely Large Telescope, and the LISA Gravitational Wave Observatory in space, will allow us to probe black holes in ways never before possible. We may soon detect the gravitational waves from supermassive black holes merging in the early universe. We may watch the birth of black holes from dying stars in real time. We may even begin to test the limits of general relativity itself, pushing into the realm where a new theory of quantum gravity may emerge. For a long time, black holes were thought to be invisible, unknowable, and purely theoretical. Now they are part of our daily scientific work. We measure their mass, track their motion, and capture their shadows. We listen to their collisions and trace their influence across billions of years of cosmic history. This transformation, from unseen mystery to observable reality, is one of the greatest scientific stories of our time. Black holes, once imagined only in the pages of theory, have stepped into the light, not by shining themselves, but by bending the light, matter, and space around them. And in doing so, they have shown us that the universe is more surprising, more beautiful, and more alive with motion and change than we ever imagined. Part 7. Black holes and the edge of physics. Do black holes hold the key to new physics? Black holes are not just cosmic oddities. They are testing grounds for the most fundamental ideas in physics. They are places where the known laws of nature stretch, bend, and sometimes snap. In the heart of a black hole, the familiar rules that describe matter, energy, space, and time begin to fall apart. This makes black holes more than just astronomical phenomena. They are doorways to a deeper understanding of reality. The most serious challenge that black holes pose is the breakdown of our current theories. General relativity, Einstein's theory of gravity, describes the motion of planets, the bending of light, and the warping of space-time. It works beautifully at large scales. But it doesn't work well with quantum mechanics, which rules the world of atoms, particles, and everything small. Normally, these two worlds don't overlap, but inside a black hole, they collide. At the center of every black hole lies a point called the singularity. This is where matter has been crushed into an infinitely small, infinitely dense state. General relativity says space-time curves infinitely here, and the laws of physics stop working. But quantum theory says nothing should be infinite, and energy and information should always be conserved. So which is it? Both can't be right. This contradiction tells us that our current understanding is incomplete. To make sense of the singularity, we need a new theory, one that unifies general relativity and quantum mechanics into a single framework. Scientists call this goal the search for quantum gravity. Many ideas have been proposed. One of them is string theory, which suggests that particles are not points, but tiny vibrating strings of energy. Another idea is loop quantum gravity, which proposes that space itself is made of tiny loops, giving it a granular, discrete structure. These theories attempt to describe what happens at the Planck scale, the smallest length imaginable, far smaller than atoms, where both gravity and quantum effects are equally important. If we could understand black holes at that scale, we might unlock a deeper theory of everything. One of the biggest puzzles in this search is the information paradox. According to quantum theory, information, the exact state of all particles in a system, is never truly lost. But black holes seem to break this rule. When something falls into a black hole, all the details about it, its shape, its structure, its chemical makeup, appear to vanish. From the outside, all we ever learn is the object's mass, charge, and spin. Everything else disappears behind the event horizon. Then came an even stranger idea. In the 1970s, physicist Stephen Hawking showed that black holes are not completely black. Due to quantum effects near the event horizon, black holes can emit a faint glow of particles. This radiation, now known as Hawking radiation, carries energy away from the black hole. Over immense spans of time, this means that black holes could slowly shrink and eventually evaporate entirely. But if a black hole disappears and all the information about what fell into it is lost, then quantum theory is violated. On the other hand, if the information somehow escapes, then it must be hidden in the Hawking radiation. But this radiation appears random, carrying no clues about what went in. This is the information paradox, and it has sparked one of the most heated debates in theoretical physics for over 40 years. Many possible solutions have been proposed. Some physicists think that the information is stored on the surface of the event horizon, like a kind of hologram. Others believe that subtle patterns in the Hawking radiation might carry the information after all, though we don't yet know how to decode them. A more radical idea suggests that information might be preserved in a kind of hidden connection between the inside and outside of a black hole, a wormhole, or Einstein-Rosen bridge. These ideas are still being explored, but none has yet provided a final answer. As strange as it sounds, black holes might even play a role in our understanding of the early universe and the fabric of space itself. Some models suggest that tiny black holes, formed just after the Big Bang, could help explain the mysterious dark matter that makes up most of the universe's mass. Others propose that black holes might be involved in the creation of new universes, that when a singularity forms, it might cause a kind of bounce, creating a new bubble of space-time on the other side. Another fascinating idea is that black holes could be natural laboratories for testing new laws of physics. As we observe them more closely, through gravitational wave detectors, radio telescopes, and high-energy observatories, we can look for tiny deviations from Einstein's predictions. If we find any, they could be signs of a deeper theory at work. Already, data from LIGO and the Event Horizon Telescope are being used to test models of quantum gravity and string theory. But we don't need to go to other galaxies to do this kind of science. Some physicists are exploring the possibility of creating artificial black holes in the lab, not with real gravity, but with analog systems. In certain materials, waves of sound or light can behave like particles falling into a black hole. By studying these systems, scientists can simulate Hawking radiation and other effects, giving us insight into how the real thing might work. At the same time, computer simulations and theoretical models are pushing the boundaries of what we know. Supercomputers can now model the complex behavior of merging black holes, the formation of accretion disks, and the twisting of magnetic fields. These simulations match closely with the signals we see from space, adding confidence to our theories and helping us improve them. Black holes are not just the end of stars. They are the edge of knowledge itself. They challenge us to rethink space, time, matter, and the very idea of reality. They demand that we bring together the best of all our scientific ideas and show us where those ideas fall short. Perhaps someday, a complete theory of quantum gravity will rise from the paradoxes and puzzles that black holes reveal. Perhaps we will discover that black holes are not the final stop in the journey of understanding, but the beginning of something far more profound. A window into a deeper structure of the universe we have only begun to imagine. What is certain is that black holes, once thought to be invisible and unreachable, are now central to the future of physics. They are cosmic riddles written in gravity and light. And as we continue to listen to their signals, trace their shadows, and explore their edges, they may finally show us the shape of the truth beyond the horizon.